in any case, so here's figure 4.1 from your text. And I'll turn the lights on so you can actually see a little bit better. So, what's that? So anyway, this shows the shows spherical coordinates, right? So here's r and theta and phi, as we've said before. And then this is supposed to be in 3 dimensions. So r hat is the unit vector which points directly away from the origin, from point P. So we've drawn them detached from point P, but this triad of unit vectors is really supposed to be at point P there. We just separated them for clarity. And then theta hat is perpendicular to r hat and points in the direction of increasing theta. So in other words, if you imagine taking this r here and thinking of it as like a meter stick or something, and then you pivot it a little bit so that only theta is changing, then it sweeps out a little displacement in the direction of theta hat. So theta hat points in the direction where only theta is changing, and locally phi and r are staying constant. Of course, if you keep going, then that can change or whatever. But actually, it wouldn't. No. So yeah, it's pointing in the direction where only theta is changing, essentially. Yeah, what I mean is, is that theta hat itself, if you literally moved along theta hat, you are getting a little further from the origin. But we're talking about instantaneously, just a little tiny displacement in the theta hat direction has r and phi constant, and only theta is changing. And then phi hat is similar. Phi hat is pointing in the direction of increasing phi. And so if you imagine taking this and thinking of it as like a rod and pivoting it around the z-axis so that theta stays constant, and certainly the length of the rod stays constant, then it's moving in the direction of phi hat. So phi hat's really kind of into the paper here, and then theta hat is down and r hat is out away from the origin. That's the triad of unit vectors in spherical coordinates. And as far as the displacements are concerned, here, this is actually taken from our astrophysics book, which is being used to illustrate something else. But if you think of this as a little patch on the surface of a sphere, and think of this as the radius vector, the displacement from the origin of length r, then if I move a direction, if I move in the theta direction by an angle d theta, what is the length of this arc right here? So if this is r and this angle is d theta, what's the length of that arc right there?
R d theta.
That's r d theta, right? So that's why the displacement in the theta hat direction is r times d theta. It's not shown here, but if I move straight out from the origin, a distance dr, well then the distance I've traveled is dr. I don't need to multiply, but theta is an angular coordinate, so I have to multiply by r d theta in order to make it a distance. r is already a distance, so dr is the displacement in the radial direction. And then here, if this angle right here is d phi, then what is the length of this little displacement right here? This is r, this angle is d phi, what is this displacement? It's not r d phi because the arc is being swept out of a circle of radius given by the length of this thing right here. What is this distance? If this is r, here's theta, that's really perpendicular to the z-axis up there. It's just that this is a perspective drawing. So that's r sine theta up there. I'm not quite told, but r sine theta, all right? And if that angle's d phi, what's that distance right there? R sine theta d phi. So the 3 displacements are dr r hat, that component, then r d theta times theta hat, and r sine theta d phi times phi hat. That's why dr, the little displacement vector, has those 3 components. Dr in the radial direction, so dr r hat, plus r d theta in the theta hat direction, plus r sine theta d phi in the phi hat direction. So the gradient vector, therefore, has components that are sort of like the reciprocals of those. In other words, this is sort of like taking 1 over dr, 1 over r d theta, 1 over r sine theta d phi. But they're derivatives, and so we're taking the change in the function divided by those displacements. Just like in Cartesian coordinates, it's change in function over change in x alone is the partial with respect to x. Change in function over change in y alone is the partial with respect to y, etc. Same sort of thing here in spherical coordinates. That's what the gradient vector looks like. Now, I will figuratively turn Alex's head. And zoom his vision out. And continue merrily along our way here. So now we've got the expression for r in the coordinate basis. We've got the expression for grad in the coordinate basis using spherical coordinates. So that means we can write down the expression for the angular momentum vector operator in spherical coordinates. So classically, the angular momentum vector is with respect to a given origin. So there's the origin. Here's my particle. It has some momentum p, displacement r from the origin. Hello. The angular momentum with respect to the origin is what? L equals r cross p. That's the definition of angular momentum. L is equal to r cross p. That's what we used before to get the expression in Cartesian coordinates for the angular momentum operator components. We took minus IH bar r cross the gradient operator. We're going to do the same kind of thing here. As an operator, L is the operator representing position cross the operator representing momentum, or in other words, it's in the coordinate basis. So I'll put an arrow to say representation in the coordinate basis of r cross minus IH bar grad, because in the coordinate basis, minus IH bar gradient operator is the momentum operator. So then we take minus AH bar, and then we take r, which in spherical coordinates is r times r hat, and cross it with the gradient vector operator, which is this beast right here. So we cross r hat with r hat partial with respect to r operator plus theta hat 1 over r partial with respect to theta plus phi hat 1 over r sine theta partial with respect to phi. So if I carry that through, that gives me minus IH bar times r times r hat cross r hat, partial with respect to r, plus the r that multiplies r hat in vector r cancels these 1 over r's in the angular pieces of the gradient operator. So I get plus r hat cross theta hat times partial with respect to theta plus r hat cross phi hat times 1 over sine theta partial with respect to phi. stick. So I can do this in 3 dimensions. Oh look, there just happens to be a 2-meter stick right here. What an amazing coincidence. And I have here r hat. Should we go with blue or green for theta hat? You can give me a choice. Theta hat should be blue. Okay, theta hat, now I have to remember that. Theta hat is blue. And phi hat is green. Phi green. Okay. And r red, r hat. Alright? So here's my unit vectors. The origin will be in this corner right here. We'll ignore the fact that architecturally we have this little thing here. And so we'll just pretend this goes all the way, you know, like so. So here's the x-axis, the z-axis, and then a y-axis, which is along this direction right here. Okay, just like in the picture. Here's point P. Here's point P right there. So the meter stick here, the 2-meter stick represents R, the one that has the arrow over it. So it represents that beast right here. Okay, so there's R hat, the unit vector, pointing directly away from the origin. And then theta hat is blue. So theta hat looks like that, perpendicular to r hat. And if I were to swing this thing so that it's only changing its theta value, then it's swinging in the direction of theta hat. So there's theta hat. And then phi hat is that vector right there. Because if I swing this thing so that only phi is changing, then I'd be swinging in the direction of phi hat there. So r without the unit vector on it, without the hat, r hat, theta hat, phi hat. Okay, now we've got cross products of r hat cross r hat, r hat cross theta hat, r hat cross phi hat. What is r hat cross r hat? 0, because like any self-respecting vector, and even those which don't respect themselves, its cross product with itself is 0. What if I take r hat cross theta hat? Yeah. If you take r hat cross theta hat, you get phi hat, because here's r, here's theta. I'm out of hands. I'll use my right-hand rule now that I've cleansed everything. Okay, so r hat cross theta hat points in the direction of phi hat. And there's a 90-degree angle between them, and they're both unit vectors. So the magnitude is 1 times 1 times the sine of 90 degrees, right? So in other words, r hat cross theta hat is in fact phi hat. Meanwhile, what is r hat cross phi hat? R hat cross phi hat, my thumb is pointing in the direction opposite to theta hat. So r hat cross phi hat is equal to minus theta hat. Yeah, r hat cross phi hat is minus theta hat. And that's probably out of the view of the camera. So now suddenly it's in view of the camera, where we see that r hat cross theta hat is phi hat, and r hat cross phi hat is minus theta hat because it's going in the other direction there. Okay? So that lets us simplify that expression that we just wrote there. So we'll write that down. I'm not going to try to draw a picture. That's why I did it in 3 dimensions, because it's hard to draw. But I'm hoping you can visualize, or even look carefully at figure 4.1 and visualize. So, but this is following from this. I just want to write down there. We have that r hat cross r hat is equal to 0. That r hat cross theta hat is equal to phi hat, and that r hat cross phi hat is equal to minus theta hat. So we get to toss that first term in the L operator, And the rest of it, we can say L is minus I h bar times phi hat partial with respect to theta minus theta hat times 1 over sine theta partial with respect to phi. Just using the fact that r hat cross phi hat is theta hat, and r hat cross theta hat is phi hat. R hat cross phi hat is minus theta hat, r hat cross theta hat is phi hat, r hat cross r hat is 0. Notice that L only involves angular variables. The r completely dropped out of it, so it only involves the angular variables, which is not surprising, I hope, because angular momentum is about orbiting, as you know, kind of fundamentally. I mean, you can move in and out, but it's only the component perpendicular to the radius vector that contributes to the angular momentum when you do the r cross p business. All that matters is the component of p perpendicular to r, and so therefore it only involves the angular variables. So let's draw a preliminary box around that so that we'll note that. Okay, any questions? Let's see here if I can pull that out for a moment. That tickles. I'm going in the right vectors. Not just a flat screen there. Okay, anyway, now more vector prestidigitation. Phi hat is also equal to, well, okay, I should have probably left that there, but I'll draw this. Okay. Phi hat is equal to z hat cross r hat over the magnitude of z hat cross r hat, because there's x, y, z, there is r, there is theta, so there's z hat. Actually, there's z hat, but then also I'm allowed to do this. Here's z hat. I'll just draw a copy of z hat at the tip of the arrow. And here is r hat. And I hope you can visualize that if I take z hat cross r hat, which direction does that point? Kind of generally inwards. If this was really on the YZ plane here, it would be pointing into the board. If it's not, well, it's doing something like this. So if I take z hat cross r hat, it's perpendicular to both of them. Happiness. And in fact, it's azimuthal. It's pointing in the azimuthal direction, the direction in which phi is increasing. It's in the phi hat direction. So see if you can convince yourself of that. Now, why am I dividing by the magnitude of z hat cross r hat here? Why isn't it just z hat cross r hat? Yeah, I want a unit vector. I want a unit vector, and z hat and r hat don't have a 90-degree angle between them. They have an angle of theta between them. Copying just from the origin down there, there's an angle of theta between them. So I have to cross them and then divide by the magnitude in order to turn that into a unit vector, because z hat cross r hat points in the phi hat direction, but it's not a unit vector, so I have to divide by its magnitude. So what is the magnitude of z hat cross r hat? Well, it's the magnitude of z hat times the magnitude of r hat times the sine of the angle between them, right? So it's divided by sine theta, because those are both unit vectors, so product of the magnitudes is 1, times the sine of the angle theta between them, which is their magnitude. And I can write out what z hat cross r hat is. in Cartesian coordinates. I'm going to write phi hat in its Cartesian components, which, as we'll see, is a very useful thing to do, because we're going to want to talk in terms of Lx and Ly and Lz in terms of Cartesian. We want Lx, Ly, and Lz in terms of spherical coordinates, but Lx, Ly, and Lz are Cartesian components. So we want Cartesian components in spherical coordinates, which sounds crazy, but it's useful. We want this. But, and, okay, I am going to do that in a moment, and z hat cross r hat, we can find by constructing the determinant x hat, y hat, z hat along the top. What are the components of z hat in Cartesian coordinates? 0, 0, 1, right? So 0, 0, 1. Leave yourself plenty of room along the bottom there. I hope you have, otherwise erase and make your matrix wider. What are the components of r hat? Remember, r is equal to x hat, but x is r sine theta cos phi x hat. And what is the y component of the position vector r? What is the x coordinate? Sine theta sine phi. So we got r sine theta sine phi y hat. And what's the z component? Plus r cos theta z hat. Those are the components of vector r. So what are the components of unit vector r hat? Well, it's vector r divided by its own magnitude. R hat is vector r divided by the length of r. So the components of r hat are just the same thing, but you take the r's off. Its components are sine theta cos phi x hat, sine theta sine phi y hat, cos theta z hat. So along the bottom row, I write sine theta cos phi for the x component of r hat. I write sine theta sine phi for the y component of r hat. And I write cos theta for the z component of r hat. So what do I get for the x component of the cross product? Almost. I have a minus sign there because I have to do 0 times cos theta minus 1 times sine theta sine phi. So I get x hat times minus sine theta sine phi. And for the y component, I get what? Sine theta cos phi, right? I go 1 times sine theta cos phi minus 0 times cos theta because I do the determinant in the reverse direction when I move to the middle of the top row there. So I get plus y hat times sine theta cos phi. And what about the z hat component? The z component? 0, because I've got 2 zeros there. So it's only got x and y components. But that makes sense. Phi hat better darn well have only x and y components because phi hat
is a function of x and y.
Phi hat is parallel to the floor. If you think carefully about it, it's the azimuthal unit vector. It's parallel to the floor. It's parallel to the xy plane. So it has no z component. It only has x and y components. A careful drawing can allow you to deduce this just from your drawing, but I'm being systematic in writing it out because it's really hard for me to draw it convincingly enough to convince you of that, or this would take a while. This took a while too, but it wasn't horrible. So, since phi hat is z hat cross r hat over sine theta, the sine thetas drop away there, and phi hat by itself is simply given by minus sine phi x hat plus cos phi y hat. Oh, well that's nice. So notice what we've done there is we've expressed the polar unit vector phi hat in terms of its Cartesian coordinates, but we wrote those Cartesian coordinates in terms of spherical coordinates, right? So, but that's okay. It's a perfectly legitimate expression. And then once we've got that, we can figure out what the components of theta hat are. And the reason we're doing this is because we're going to want to plug into that expression that we got for L in terms of phi hat and theta hat, put it in terms of x hat, y hat, and z hat, and then we'll be able to read off the components of the angular momentum operator written in spherical coordinates. And if you're like, given blobbin, florbin, flobbin, what? Well, it'll make sense when we actually do it. So, meanwhile, then, so we found the expression for theta hat, for phi hat. Theta hat is equal to, well, let's reverse the order. It's equal to phi hat cross r hat, right? Because r hat cross phi hat was minus theta hat. So we'll reverse the order and say theta hat is phi hat cross r hat. But now we know what the components of phi hat are, and we already know what the components of r hat are. So we can say now then that we're going to take, I'm going to write the bottom row first because that's the biggest things there. So the components of r hat again haven't changed since we last met them. Sine theta cos phi for the x component, sine theta sine phi for the y component, cos theta for the z component. Meanwhile, phi hat's components are minus sine phi, comma, cos phi, comma, 0. So minus sine phi, cos phi, 0, and then along the top, x hat, y hat, z hat. This is the cross product that we must take. No dividing by the magnitude this time because I'm constructing it directly from the unit vectors that are perpendicular to one another. So I could divide it by its magnitude, that would be divided by 1. That would be silly. So if I take that, for the x hat component, what do I get? Yeah, cos theta cos phi, right? Cos theta cos phi. We get cos phi cos theta minus 0 times sine phi sine theta. And then for the y hat component, what do I get? Yep, I get 0 times sine theta cos phi minus sine phi times cos theta. So I'm going to get cos theta sine phi time for the y hat component of theta hat. And then I'm not putting the sign in yet. What is going to be the z hat component there? For the z hat component, I'm going to get minus sine squared phi sine theta minus cosine squared phi sine theta. What is minus sine squared phi sine theta minus cosine squared phi sine theta? Just minus sine theta, using the fact that sine squared theta plus cosine squared theta is 1. So our phi, I meant to say for that last part. So I just get minus z hat times the sine of theta. Any questions? So now, it's time for the payoff. said before, we had deduced that L was equal to minus IH bar times phi hat dd theta minus theta hat times 1 over sine theta dd phi. But now I can go nuts expressing phi hat in terms of x hat, y hat, and z hat, and theta hat in terms of x hat and y hat, and then group terms like so. So here goes. So this is equal to minus IH bar times open square bracket. So I'll plug in for phi hat, I'll plug in minus sine phi x hat plus cos phi y hat. And that's all multiplied by the partial with respect to theta. Minus, and now in parentheses I'll write out what theta hat is in terms of Cartesian coordinates. So minus cos theta cos phi x hat plus cos theta sine phi y hat minus sine theta z hat times 1 over sine theta d phi close square parentheses, close square bracket. Well, L is also L sub x, x hat, plus L sub y, y hat, plus L sub z, z hat. So I just read off Lx, Ly, and Lz here. In other words, the things collectively which multiply Lx, which multiply x hat, I should say, the things collectively which multiply x hat is the expression for L sub x. Collectively, that which multiplies y hat, all that collected together is L sub y, and all that multiplies z hat collectively is L sub z. So, let's do such collection. When we do, we find that L sub x is equal to IH bar times sine phi dd theta plus cosine of phi cotangent of theta dd phi. The reason we're getting a cotangent of theta is because notice over here we've got cosine theta over sine theta multiplying dd phi. And so therefore these guys get together and make a cotangent of theta. And then notice this is minus, minus over here, and minus, minus over here, which is why it's just pluses over there, because in both terms you've got minus, minus, which is plus. For L sub y, if we collect the terms that multiply y hat, for L sub y, we get IH bar times minus cosine phi, partial with respect to theta, plus the sine of phi times the cotangent of theta times the partial with respect to phi. And for L sub z, and this should come as no surprise, we found L sub z by just using the chain rule before. You could use the chain rule to get the expression for Lx and Ly, but you'll hurt your head if you try to do that. This method turns out to be easier. advanced method gives it as a byproduct, but it was easier to just transform the partial derivatives. But we can read off that L sub z here, that's easy. There's only one thing that multiplies z hat, namely, we've got minus, 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 so it all adds up, so it all multiplies out to minus IH bar dd phi, because the sine theta there is canceled one another. So L sub z is minus IH bar dd phi, just like we got before. Only now, with this, we also got Lx and Ly written in spherical coordinates. So why would we want such a thing? Because it's easier to solve the problem in spherical coordinates, and then if we happen to want what's the x component of the angular momentum, things like that, well, if I've got the wave function written in spherical coordinates, I'd like the operators in terms of spherical coordinates. So, boxy, boxy, boxy. Yourself, if we find the expressions for L plus minus, so in other words, first plus then minus, remember that's equal to Lx plus or minus I Ly. What you get is that L plus or minus is plus or minus h bar e to the plus or minus I phi times dd theta plus or minus I cotangent of theta d phi. And if you're saying, where the hell did e to the plus or minus I phi come from here? It's because you will see the following combinations when you take L plus and L minus by adding Lx plus or minus I Ly here. You get the combination of cos phi plus minus I sine phi when you do that, which is e to the plus or minus I phi. Because here we've got a cos phi that we're going to take in. You know, if I do plus I Ly, I'm basically going to go cos phi plus I sine phi type of thing, multiplying cotangent theta. When I do it as a minus, I'll get a cos phi minus I sine phi times a cotangent theta. And so notice the plus or minus signs here. In other words, what an expression like this means is to get L plus, read along the top. So L plus is h bar e to the plus I phi dd theta plus I cotangent theta dd phi. L minus is, well, notice it's minus h bar e to the minus I phi dd theta minus I cotangent theta dd theta. So you read along the top for L plus, you read along the bottom for L minus. This second term, notice, is really the same ultimately in both cases if I factor, if I expand it out, because here I'm getting plus, plus, here I'm getting minus, minus. So in both cases, the second term becomes h bar e to the plus or minus I phi, I cot theta dd phi, whatever. But anyway, that's what you get when you collect out what L plus and L minus are in terms of spherical coordinates. Which is great, because that's what we're going to need. If we could find what the LL state is in terms of spherical coordinates, and we will, you can keep hitting with L minus written like this in order to generate all the other states. So you get YLL, the spherical harmonic LL, and then L comma L minus 1, and then L comma L minus 2, all the way down to L comma minus L. So that's why we did that, because we want to be able to hit angular momentum eigenfunctions with the raising or lowering operators. But since we're going to write them in terms of spherical coordinates, we want the raising and lowering operators in terms of spherical coordinates. And there they are, beautiful as they be. In problem 4.21, which you're going to do after Thanksgiving break, in problem 4.21, you will joyfully show that from all this, the L squared operator is in fact what we claimed it was before, only now you'll have shown it. That L squared is in fact minus h bar squared, 1 over sine theta d theta sine theta d theta plus 1 over sine squared theta d squared d phi squared. So using all this stuff, we'll be able to show that L squared does in fact have that expression in spherical coordinates, which is ultimately easier than trying to transform the derivatives would be. That's another way to do it, but transforming the derivatives will hurt your brain, trust me. You'll make 7 mistakes and give up. You'll make 5 mistakes and give up. Maybe you'll do the whole thing, and then my hat's off to you, because boy, it's hard to do that without making mistakes. The simultaneous eigenfunctions L squared and LZ, those operators, are called spherical harmonics, which of course has to be written like that, or YLMs. So in other words, people just say YLMs. Why do you call them YLMs? Because that's how they're written. So the functions in the coordinate basis, which represent eigenfunctions of the L squared and LZ operators, which we've written expressions for here. Here's LZ, there's L squared. The functions of theta and phi, which are eigenfunctions of those two operators simultaneously, are called y subscript L superscript m. Some books write y L comma m instead, but physicists like to write y sub L super m. So L squared applied to that function gives L plus 1 h bar squared times the function. So in other words, that L is playing the role that it had before in our algebraic demonstration of the eigenvalues. And L sub z applied to YLM of theta and phi is equal to m h bar YLM of theta and phi. For a given value of L, m ranges from what to what? Minus L to L, right? In steps of 1, absolutely. M ranges from minus L to L in steps of 1. Good, that has been drummed in. That's what we have found. So we have, let's make a list of pairs of possible subscripts that can decorate our capital Y's there. We have, there is Y00 is a possibility of theta and phi. I'm not going to keep writing of theta and phi. Y00, and then there is Y11, comma, Y10, comma, Y1 minus 1. Those are the 3 YLMs for L equals 1. There's Y1, Y0, Y minus 1. For Y2, there's, for L equals 2, there's Y22, Y21, Y20, Y2 minus 1, Y2 minus 2, let's put that in chemist speak. What does a chemist call states where the angular piece is Y00?
Ground state.
If n is equal to 1 for hydrogen, that'll be the ground state, but you could also have n equals 2, and L equals 0, and M equals 0. S. These are the S states. Yep. These are the S states. What's the S state, I should say? There's only one of them. So, jumping ahead to hydrogen, you've got 1s, 2s, 3s, 4s, and there's only one S state, which can have spin up or spin down in it. Chemist speak for these guys is P states. Yeah, these are P states. Chemist speak for these guys is D states. What are the next ones?
F states.
F states. And then things suddenly become sensible. G states, H states, I states. There's no J states, if I recall. You skip J. Starting to sound like astronomers. Skip J, go on to K, or whatever. But usually, S, P, D, F are the ones you're most interested in. So, and do you know what they actually stand for? It comes from ancient spectroscopic notation.
The guys who discovered the spectrum, the spectrums.
No, it's not named after people.
Oh?
Nope. S stands for sharp, P stands for principal, D stands for diffuse, and F stands for something else. Fold, I think, or something. I can't remember what F stands for. Don't be too creative trying to think what F stands for. SPDF. So sharp, principal, define. Sharp, principal, diffuse, and fine. It was based on the appearance of spectral lines.
That was just back in that.
Yeah, it's depend on they named it based on the appearance of spectral lines involving transitions
Just back in
with the states.
Back
Yeah.
in physics.
Yep, that's where that comes from. Yep.
Just back in physics theory, I remember the Lyman series.
Yeah, there's the Lyman series, the Balmer series, the Paschen series,
All of
the
them.
Brackett series, the Fund series. Back then, the fruit was hanging low, and you could get a series named after you. They were just there for the taking. Just find a series of hydrogen lines and name it after yourself. Principal. Yeah. So sharp, principal, diffuse, and fine. So the F stands for the same thing that it does in RTFM, which everyone knows stands for Read the Fine Manual, which is what you say to somebody when they ask you a question, and they could know the answer if only they would have read the fine manual. Only the F doesn't actually stand for fine. But this F really does stand for fine. So. Okay, looks like it's time to give it a rest for today. So. I do. I have to at 3:30.